各位同学，那我们就开始今天演讲。我们今天很高兴邀请到我们的系友翁鹏杰博士，然后来帮我们做演讲这样。那因为今天我们有一些那个外国学者在这边说，他可能会用英语演讲这样，那我们欢迎他。
Thanks for introduction, and it's my great honor and a privilege to be here to give this talk. And today I will talk the nearly nilpotent groups and the Langlands reciprocity conjecture. And somehow this title is somehow misleading in the sense that I think I will spend around most of time to motivate us and try to describe why we need the notion of the nearly nilpotent groups. And if time allows, I will go through some parts of the proof of the Langlands reciprocity conjecture for the nearly nilpotent Galois tension. So let us start by let me review or recall some basic notion of the group theory. So, as far as we know that if you want to study certain type of mathematical object, we want to have a certain lovely structure, and probably the easiest one is the group structure. And so here, but in general, group essentially we have two types of groups. The one type is called a solvable group. It's much easier, and another type is non-solvable. But among the all solvable groups, we also have some notion to distinguish the different type of solvable groups. So the zero is the cyclic group and the abelian. So most of this talk, I will only assume the basic knowledge from the undergraduate level algebra. So I assume everybody knows that a cyclic group is a group with the element generally a whole group, and the abelian group is that all elements just commute. So now we have one. So here is the program symbol is a C1 or trivial group, C2, the cyclic group of all the two. But once we go further, we have some notion to generalize what is the cyclic and the cyclic group and some kind of generalization of abelian group. Is that we consider S3. S3 probably is the most delightful group that it's pretty small. It's only a group of all the six, but it is non-abelian. And so that is non-cyclic. However, we know that C3 is no more in S3. And it's easy to just check order. It's isomorphic to C2. So now you can see that we decompose our S3 into two layers. The first one is a cyclic group, another one is also a cyclic group. So essentially it's just consists of the two cyclic groups. So we have a name for this type of group is that. So S3 is called a metacyclic. And the more metacyclic. Okay. So by metacyclic group, we mean that you can find a cyclic normal subgroup such that the quotient group is also cyclic. And by meta-abelian, we mean that you can find an abelian normal subgroup such that the quotient is the abelian group. So let me write down it. Let me only write the definition for meta-abelian. So if we can find a normal subgroup inside G, such that N and the G quotient N are both abelian. So you can see that it's the first example or first generalization of the abelian group. And however, if we move a little further, so again, we look at the symmetric group, but now we look at the symmetric group on 4 letters. So we consider S. Fortunately or unfortunately, we know that so if we G equal to S4, so we know the G prime, the third subgroup is A4. And the G double prime is isomorphic to the Klein-Four group, or isomorphic to C2 group. So you can check that here, S4 cannot be a meta-abelian group. So imply S4 is not meta-abelian. So now we have a notion of the cyclic groups and the abelian groups and the meta-cyclic and the meta-abelian. Okay. So you might wonder why we care about this generalization. There is a quick fact that every solvable group you can always realize it as a Galois extension over the rational numbers. So every group pop out here, you can consider it a Galois group over a certain Galois extensions. And if you want to study the number series, this type of Galois extension or Galois is pretty important. Okay. So, however, you can see this type of group is all of these groups are solvable. So, I mean, so we have a notion probably which is the 0 prime. So and then you can, the reason why we need this notion is the following. You can see every group pop up here. They are all solvable. You can just check that they have the subnormal series, and such that each quotient is just abelian or cyclic. But you can see the cyclic groups. The natural cyclic is pretty far from the natural symmetric group of 3 letters or 4 letters. And once we want to study these types of things, then we need a certain net to name it, and so that we can capture the property of that. So let me give you the property 3, and the probably the most important thing in our talk is the nilpotent. G is called nilpotent. So the story is the following. You can see we want to generalize the notion of the abelian groups, but we do not want to generalize that too much. For example, because you can see, if we generalize the abelian group as the solvable groups, we know that every finite group of order at most 59, they are all solvable, but they have a completely different natures. So we have the notion called the nilpotency. If one of the so first thing is that G omits central series. Namely, we have this change. So from the 0 equal to 0. Such that first, each GI is known in G. Second, we know the GI plus 1 or the GI is inside the center of G. So probably this one is the most technical definition. So we have another one too. It's much easier to check is that G is a direct product. So this one is probably the most useful the condition. Because you see, now it means that every zero subgroup in G is normal inside. So essentially we just decompose it as a product. So roughly speaking. So G looks like this one. So the use of this notion is that when you decompose your group as a product of the zero subgroups, so we know that from this you can see that once you have two elements, they have the coprime order, they commute to each other. Because once they have coprime order, they just lie in the different, if you decompose it. So in that case, you can see that the nilpotent groups, they are almost abelian once you do this decomposition things. And the third one, probably the most weird one, is every subgroup H is subnormal. Okay. So essentially, what you have is that is you have H equal to H now. That's left. Hi. No. So you can see the third condition in fact is another generalization of the abelian groups, because we know that every group, well, every subgroup in the of abelian groups is normal, and this one is somehow the much bigger condition. Great. And so the example is that if G is equal to prime order, then G is equal. So you can see this one, in fact, if you just check the second condition, this example is trivial, because if you have G is equal to, the order of G is equal to the prime order, itself is just the zero subgroups. So you always have this decomposition. And however, you can see this one, so, and the non-nilpotent. And another non-example is the S3. S3 cannot be nilpotent. The reason is that if here, the C2, this 0,2 subgroup of S3 is normal, you can decompose our S3 into a direct product of C3 and C2. And in that case, that means that S3 is abelian, but it's impossible because we know that S3 is the first non-abelian finite group. Okay. So as you can see that you might check this one, this S3 and S4 and so on and so forth. Like we can check the whole finite group of order at most 59. They are all solvable. Essentially, we are using the zero series, and also we use some just by counting. And however, somehow it's not the most efficient way to do the group here. So to study the groups, some mathematicians, I believe, including the Burnside and Kelly, they figure out another brilliant way to study the groups. Namely, we are using a certain type of a group homomorphism. So let me recall probably one basic fact. If you do the group action carefully or use the pigeonhole principle carefully, you can always embed any finite group into the symmetric group on n letters just by the easy exercise. However, you can see that somehow this basic fact told you that you can always embed any finite group into a symmetric group on natures. However, you can see, however, this is not a good way to do, because, for example, if you want to study the subgroup groups, and then you embed this subgroup group into the like S5, but it's well known that S5 is non-solvable. So you can see that these two groups, they have the completely different group theory nature. So that's not good. So we will do the following thing. We will do that. V complex. Vector of dimension n. So the trick here is that we consider the group homomorphism between our finite group into the group of non-singular linear transforms. Representation rho of G is a group homomorphism from G into GLP. Oh, well, if you want GLP. So, and let me write down the topic. So, linear. The character is defined. Okay. So let me say something about this notion. Let me tell you why we care about this type of group homomorphism. So first thing is that because this one is group homomorphism, so it preserves all information from our finite group G into some well-known or somehow much easier to study type of groups. Because we know that GLNZ is all non-singular linear transform or non-singular linear matrices. And we can always do some numerical computation to know the properties here. And on the other hand, because it is a group homomorphism, so each representation will tell us the part of information of our group. And so the trick here is that we want to utilize all these type of group homomorphism to recover certain type of information of our group. And somehow, or it turns out that it's even easier to study the character. Then you just take our trace of our rule. And then this one is well defined because we know the trace is stable under the conjugation. And so no matter how we pick this isomorphism by choosing the basis, this one is well defined, so it's fine here. So once we have this notion of representation, so now, and just keep in mind that our goal is study a group. And here's the thing. If there are infinitely many representations, in some sense, it's pretty bad. Because now you need to study infinitely many group homomorphisms to recover the information of the finite group. So they might not be a good thing. So we need to some notion to simplify our consideration. So the consideration is the following. We want to decompose our vector space into a subspace. So the trick is that if we have rho and S on G, S on top, so we have the subspace W inside the subspace V. And we want to construct some representation over this W. So the trick is that we require this for every G and for every V. So now first thing is that our rho is a group homomorphism from G into a GLV. So for sure it's a linear transform over W. So this one, in fact, you can see essentially is GLN. And secondly, so it acts on W naturally, but you can see this might not always be the case that this one will send the W back to the whole space. So we need to require these things. So once you can these things that implies G can be over down. So in other words, what happens is that every G row of G just looks like something into it. And this one gives you something inside of it. So here you can see that we decompose the row into the two representations over the W and the W curve. So we are saying that if there is no such row is called irreducible. So you can see suggest by name that the irreducible representation is that you have no way to find the subspace and satisfy this property. Because once you have this property, you can always decompose our representation into two parts. So we just said, okay, we cannot find this one. And on the other hand, here's a trick that because we know that our original space is a finite dimension here. So you can see, you just repeat this process that you can always decompose our representation into the irreducible one. Because once you have this one, you will decompose it two parts, and each part will give you a certain type of certain number of dimensions. But we can only have at most dimension n. So is that, and so we must every representation is a direction of irreducible one. So now you can see that the good thing is that we have a certain notion, or probably I should say in this way, is that to study the all type, all representation, it's sufficient to study the all irreducible one. Because we can always construct every representation as a direct sum of the irreducible representations. So now keep in mind, I told you that we do not want to have too many representation, or more technically irreducible representation, because they will make us or our studies harder. So so we have let me recall the following facts from the character theory. And probably that is, you will see that's why we care about this type of group homomorphism. Is that 0. Is that number of irreducible is equal to the number of conjugated class. Okay. So this one is a perfect factor. It's really easy to check, but this one is perfect in the sense that we completely control the number of the irreducible representations, and we know how many, just count the conjugated classes. So as I told you, we want to use this type of group homomorphism to recover certain type of information for our finite group. So this one. And the second fact. Second fact is that we denote I is a fact. So irreducible character is the character of the irreducible representation. And here, if we have this fact, we have this wonderful identity. Is that if you square your character degree here, and they will equal to your order of G. So you can see that somehow you know some certain type of information from your irreducible characters or irreducible representation. You can recover certain type of information for your original group. And now, if you look at the 0 and 1 carefully, in fact you know one further thing. If you have the 0 and 1 and then use the Cauchy-Schwarz inequality, immediately you will get this thing. G is abelian if and only if for every chi. Chi 1.
Excuse me, the identity or identity.
This one. Oh.
Yeah, the tile 1.
Tile 1, no. Tile 1 is the here of probably the bad. Let me write here. This one is the identity of G, and this one is the real number 1. So the thing is that because we know the number of the irreducible representation is equal to number of the conjugated classes. And we know that if your G is abelian, every element just form a conjugated class in G. So you just use this one and use the Cauchy-Schwarz identity or inequality carefully, you will get this back. So in fact, you can see this one is pretty powerful in the sense that we characterize the all abelian groups in a different manner, in the somehow easier or harder way to explain in this way. So you can see that now we made a second generalization for third one, so third generalization over the abelian group. Just let me recall, the first one is that, the first generalization is that we have the 2 layers of abelian group, and we have the meta-abelian group. And the second one is that we consider the nilpotent groups, and in that case, every element, or every 2 elements, they have the coprime order, they commute. And then you can see the third one, we can have a certain type of generalization. Just like, how about we weaken the constituency? How about we consider the group with all irreducible characters with a degree at most 2? So this question in fact was answered by the Armin. So we have pause. I believe it's around 1965 that if G is a finite group with stop. Okay. Type 1. Then G is solved. And in fact, is a weaker form of his propositional theorem. In fact, he characterized all these type of group. For example, in fact, G is either abelian or in fact it has a normal abelian subgroup with index 2, or it has a pretty large center. But for our purpose, we only need a subgroup. So,
is there a necessary sufficient condition?
Yeah. In fact, he characterized all these type of group, and in fact, I can write it down completely. But probably, yeah. In fact, this one is weaker one. In fact, he can just write down all these type of groups. There are only 3 types of this group. So, yeah. So, let me remark that I don't have time to define it, but however, let me remark later. You can see that now you can see, at least I hope I already convinced you that as far as we can have some information from the characters, we have some information of our group. Now you can see somehow it's also pretty hard to use this method. I mean, because all this method is that we start from the some group homomorphism. So then in general, we need certain type of information of the groups to construct a group homomorphism. And probably it's not a good idea to do that way because the purpose here is that we want to use this type of group homomorphism to study our group. So there's a trick called induction. So one construct. Of precise. That's that. Is a character. And in fact, it's a precise formula for this type of thing. Is that this construction is that if you know the certain characters or representations, or if you want, you can say the group homomorphism of the here H is a subgroup. If you know something from your subgroup, and you can just construct by the precise formula to construct another character of G. And the good thing of this is that you see we have a list fact. For example, if you can find a pretty large abelian subgroup, and so we know that all its characters have degree 1. So in that case, you can just construct here, and you can construct the lots of the characters of G. So here is another proposition, and I find this proposition in some famous textbook by Isaac, but he didn't mention who really proved this one. Is that if you can find a normal subgroup in G, that's like G more than 10 is nilpotent. Let me recall one definition is that if you can decompose this quotient group as a direct product of its all zero subgroups, then every irreducible chi is induced subnormal. And so let me write down. So here, what I want to say is that chi will look like stuff from stuff in this manner. So essentially, you can see that as long as your group is pretty close to a nilpotent group, we can control every character pretty in a wonderful way. And
which related to M in any way?
Yeah. In fact, we can require with our n, we have this one, H. Yeah. And this H will contain our n. And furthermore, in fact, we have a further wonderful thing. If we restrict our precise into n, this one is an irreducible character of n. So you can see that once you can find a pretty large normal subgroup, in the sense that the quotient is nilpotent, we completely control every irreducible character of G. So from here, let me define the So from here, let me introduce a notion to describe the special case of this type group that G is nearly nilpotent. If you can find a normal subgroup inside G, that's that. The following two things. First thing is that G quotient n is nilpotent. And the second thing is that every irreducible character, let me write this. you can see the second one is somehow a pretty artificial condition. But I will tell you, I think I have time, I will tell you why we put this weird condition here. So you can see that if you look at this proposition pretty carefully, the first thing is that if you have a nearly nilpotent group, every irreducible character is induced from some character of degree at most 2, and from the subnormal subgroup. Because you can see the first condition told you this, the condition here just holds. And the second thing is that we want this one. So we just want to control the character degree of our this normal subgroup. And remark is that for what you say the corollary of the Armin-Sur's theorem. You see, because Armin-Sur proved that this type of group, if your all irreducible characters have degree at most 2, it's solvable. And we know the nilpotent groups are solvable, so it's that nearly or near nilpotent imply solvability. Yeah. And in fact, all we need here. So, okay. Now I have everything and essentially everything. So let me go to the last part. Is why we care about the representations and why we care about this type of group. And in fact, it's part of the Langlands reciprocity conjecture. So Langlands reciprocity. So to describe why the Langlands reciprocity conjecture is, we need a notion of the Artin L-function. And my apology, that is the only part I cannot tell you why we have this notion. And, it requires a little bit more on the algebraic number theory. Okay. Let capital K or little k be a Galois tangent of number fields. Number fields are just the finite extension of the rational numbers, and with Galois group Q. So now we have a group here, so Galois group is okay. And we also let the row be a representative of Q. So the Artin L-function attached to row is looks like row k over little k equal to the product defined by Euler product. So wait, if our row is nice, overall nice means that unlimited. We have our local vector. So let me say something about this L-function, and I don't think I need to record this part. Okay. Here's the thing. This L-function looks pretty abstract and pretty technical. So let me tell you probably the most famous example of this L-function is that if we take the k over little k equal to the sum just equal to some Galois extension over Q. So in this case, this weird prime of our little k is just
outside of the red line.
No. So let me write down. Yeah, little k is Q. So this little k, if this little k is Q, this weird prime here if this prime is equal to the prime, it's a rational prime. So it's just really the usual prime we have, like a 2 and 3 and 7, so on and so forth. And if we pick our row equal to the trivial representation, the trivial, by trivial I mean that it's really trivial. You just send every group element into one. So if we put these three things together, you see here, because it's trivial, so it's just one dimension, so there's no determinant here. So it implies that, or S, 1G, and whatever is 1 minus is 1 here, and the norm of this one is just P, and the minus is minus 1. So just indicate this. And if you can recognize this one, this means that our rho chi 1G K over Q is our famous Riemann zeta function.
So for a prime P, what is sigma P?
Sigma P is the Artin symbol. In fact, it is the at P. But however, you can see here, because we choose the trivial representation, so no matter how we define this Artin symbol.
Yeah, but in general, it should be an element of the Galois group.
Oh yeah, so this one up is you need to you consider the conjugate class of the Fubini automorphism of our atlas P. Yeah. So so in fact you can see that this one is not well defined. Our price is not unramified because they will only well defined. You need to consider this revision restrict to the subspace fixed by the initial chapter. But here I just now want to go through the technical detail of here. But there is another way to use the local field to define the Fubini automorphism. But let me just stop here. So, but I can give you another example. Is that so another example is that if our Galois extension is cyclotomic extension. So here, if our P is not divided by N, this is really our Fubini automorphism in the following sense. Is that this Artin symbol just sends our edge root of unities to the P top. Yeah. So and in particular, if we have this formalism, we will recover the D-shaped arrow functions in this case. So you can see this one is somehow the arithmetic construction of arrow functions. And so as I said, here we can recover the D-shaped arrow function. And as we know, like the Riemann zeta function and the D-shaped arrow function, you can always extend that to the Holomorphic function over C, and but not at S equal to 1, because we know the Riemann zeta function has a simple pole at S equal to 1. So Artin asks the following things: that can one always extend these arrow functions into the entire function? Well, I just said the Holomorphic function over the whole complex set. If rho is non-trivial and irreducible, then this arrow function is entire. Or probably I should say that this one can be extended to an entire function. However, let me just quick remark. The reason why we just avoid the situation that the rho is trivial, because we know once you have the trivial representation, you will recover either the Riemann zeta function, or for general number field, you will recover a Dedekind zeta function. But in that case, we already know that L-function is already so meromorphic, yeah, except the symbol for s equal to 1. Thank you. And so, in fact, Artin himself proved that abelian case by the is a consequence of the class field series that if dimension of this row is 1, so if dimension of row is 1, then this Artin conjecture, let me write down this case. And let me big T05. So in fact, let me remark, this one in fact is a consequence of so-called class field series. So what really happens here is that Artin in fact showed that every this type of error function, and once your row is of dimension 1, he can show that this error function is in fact the Hacker error functions. So by the work of the Hacker, we know that such error function is meromorphic over the whole complex plan, except the one possible symbol for n equal to 1. So it's pretty good. And however, I think proof this one is around actually around the 1920 to 30. And people here is that people try to generalize this idea to a general representation, because here is that essentially you can see that these representations are all abelian in the sense that you always have this one as dimension 1. So people try to generalize so-called, people also try to find the non-abelian class fields here. So this one so this one in fact probably the most profound idea was held by the Langlands. He suggested the following, that Langlands suggests, I think it's around the 1960s, is that the story was skipped by myself, is that this formalism was rewritten by the Iwasawa and the Tate independently nowadays we call the arithmetic method. So there is you consider a certain type of representation of another group and to rewrite everything but to prove the same result. So Langlands said and this pi is the automorphic representation of the Galois. So I'm pretty sure I have no time to tell you what is this notion of the automorphic representation over the general linear group over the arbitrary over the little k. What I can say is something easier. Is that if you consider, so probably let's tell you. So here is that. Let me write down the result. Is that if Okay, let me give you some remark here. So first thing is that this conjecture is valid if this row has dimension 1. And this one in fact is just nothing but the result of Artin. Well, for sure one needs the work of a tape to rewrite everything in the arithmetic language. So the second step is was taken by the Langlands and including it 2 now. They prove that if our row has dimension 2, our Artin function in fact is nothing but L function attached to the modular form. Well, as long as this row is hard and our base field is over Q. So this one is, what do I say this one? You can see that here, all I want to say is that if our base field is Q, you should regard the modular forms as a generalization of the D-shaped characters. So, and this one in fact generalizes the Artin's conjecture. And one can show that by the work of the Galois and Langlands. Once you can show the Langlands reciprocity conjecture, and then the Artin conjecture will follow. So, well, let me say something about this conjecture. This conjecture is that we care about the analytic property of our L function, and the reason why we need this type of the reciprocity conjecture is that we define our Artin L function in a pretty arithmetic nature, and in this way it's pretty easy to define because we can always define like Artin single, and we can define the Galois in nature. However, because we define it in the pretty arithmetic way, we have no way to obtain it. We almost have no way to obtain the analytic property of this one. And on the other hand, if you consider a certain type of this weird automorphic, in particular, we have the notion of a modular form. The analytic property of the L functions of modular form is somehow much easier to obtain. In fact, it's not hard to show that you can extend the L function attached to modular forms to the entire function, as long as it's not the non-CN or non-CN not induced from the trivial way. So let me say the following concept. To myself is that, however, I want to say the following. In general, it's pretty hard to show the least reciprocity conjecture. The reason why is that every result you can obtain requires a certain more general machinery code than the principle of functionality. So over there, in fact, with Langlands and the 2 now, they use the result of the thickly base change of the GL2 forms to obtain their result. So this is hard. So we are playing the easier game. Is that if K over little k is nearly and the Galois, and then Langlands reciprocity conjecture. So here I mean that once we start from some nicer conclusion on our Galois extension, our Langlands reciprocity just hold. And let me remark.
The Galois proof of the substantial.
Oh yeah. And the Galois. And the remark is the following. In fact, probably I should write down the post. So the remark is the following. Arthur and Clozel, around the 1989, they prove that if K of little k is Galois and nilpotent, so 1 minute. So let me tell you essentially how proofs go. The first thing is that, and in fact, proof gives a code. So if we let G is Galois group K over T. So if we have these things, we know if the chi is the irreducible character or equivalent irreducible representative of G, we can find precise. It's that's true. Precise. So the whole trick is the following. If we start from the nearly nilpotent groups, we can control all irreducible characters by the induction map or induced representation, and with is equal to 2. And the most lovely thing is the following. Owing to the something I already read that we recorded a nearly nilpotent groups is that you have a group such that you have the pretty large normal subgroup with this condition, with whose all irreducible characters have degree at the most 2. And by the result of our mission, we know that the normal subgroup is solvable. And we know the quotient is nilpotent. So we already know that this nearly nilpotent, for near nilpotencies, implies that, and more. So now we first noting the G is solvable. So we know that all subgroups of G is also solvable. So here, in particular, the Langlands reciprocity conjecture holds. Wholly precise. Now, the last step is that because we have this constructed, and we can conclude that chi is also automorphic. In fact, it's the work of the Arthur and Clozel automorphic induction. So probably I just said it. Then by we complete the problem. So I think I will stop here.
各位老师同学有没有什么问题？
So what is the hard part of your proof? Because you said everything follows can follow from others.
The hard part is that no, I don't think there is anything. But let me in fact I asked this question to my former advisor Ron Murphy. In fact I told him that every result here is that you just put the correct notion of the near-potency, and you know the theory of induced characters, and you know what really Langlands do not do, and you know the automorphic induction from the Arthur and Clozel.
So the concept of nilpotent is introduced by you?
Yes. And I would say the hard part probably break down into the 2 parts. I believe that almost all people in our area already know that if you can know the representation in this type, then you induce from the some representation of degree at the most 2. You have a chance to use a Langlands tunnel. But the problem is the following. Langlands tunnel, they only resolve the all essentially solvable case. So, for example, there is the one remaining case is that our projected image is isomorphic to A5. And that one is pretty hard to show. So in fact, the main obstacle here is that we need to catch up to, or we need to find a situation that we can apply the Langlands reciprocity for all this time precise. So the thing is that we are lucky here because the notion of a near-potency is that this type of groups are really solvable. Once they are not solvable, you can see we can prove here. And then we can do nothing. And the second thing is that you might wonder there is a technical part here due to the restraint of the layer theory. I mean the theory of automorphic induction to the other code. Because in fact here we need something more. We cannot choose an arbitrary subgroup here. We can only apply the theory for the subnormal subgroups of solvable groups. Without that condition, their automorphic induction will fail. So one just needs to put everything together. So, yeah. But probably the hard part is that you need to go through everything and check everything carefully.
is there a formula for delta y minus x? Y minus x.
You can use the functional equation.
Yeah, but is there a functional equation?
Oh yes.
Yes.
In fact, you can complete the Artin L-function in a similar way. You just multiply the certain type of the gamma factors, and you can obtain the essentially all Artin L-function. Or if you complete it, you will always get this form. And that is the case. So you can always complete your Artin L-functions and to get this. And in fact, I should say that the functional equation of Artin L-function in fact is one key of the Langlands reciprocity. Because in fact, what he really did is the following. He looked at the functional equation of the Artin L-function, and he realized that in fact the gamma factor in fact is L or local factor at the infinity price. And he did a similar thing for this. In fact, I believe he did to the L functions attached to modular cable, and then he compared the both sides of the L function or complete L function. So he realized that one should have this to the all primes. So, and in fact, but maybe I should say he also inspired. He should be inspired by the Taniyama and Shimura, because Taniyama and Shimura they formed this type of conjecture. For this rho, the Galois representation attached to the Ewing curves, and then they said you should find the modular forms. And so Langlands just do the more general setting. And I should say another thing here. Why we need to put a solvable here is that the key is that they need a strictly bastion. However, if our projected image is non-solvable, you will essentially you will have the projected image as morphic to A5. In this case, we don't know anything about the non-strictly bastion for this type of group. So probably let me re-answer your question again. The hardest part is that the hope or the general principle is that one should always be able to apply the Langlands functionality, even if it's just conjecture, to prove this type of result. But we don't have any recipe that when this type of functionality holds, when it's not hold. For example, here, this induction map or automorphic that is not always valid. We are just being wrong.
还有其他问题吗？没有，那我们再次谢谢。